Hello and welcome to RECode 2, an event conducted by Coding Club of PSG College of Technology. In this video, I'll delve into two intriguing coding problems and explore their solutions in Java. These problems are not only fascinating but also offer valuable insights into algorithmic thinking and problem solving skills. So, whether you are a seasoned coder or just starting your journey in programming, join me as I unravel these challenges and discover efficient solutions together. Let's dive in. And I'm Vishal. My roll number is 22I372. I'm from class BTech IT G2. The agenda of today's video is problem statement 1, intuitive approach of problem statement 1, solution for problem statement 1, and problem statement 2, intuitive approach and solution for problem statement 2. Let us see the explanation of problem statement 1 in detail. There are n cities numbered from 0 to n minus 1. Given the array edges where edge of I is equal to from, to, and weight of I represents a bidirectional and weighted edge between cities from and to of I, and given the integer distance threshold. Return the city with the smallest number of cities that are reachable through some path and whose distance is at most distance threshold. If there are multiple such cities, return the city with the greatest number. Notice that the distance of a path connecting cities I and j is equal to the sum of the edges, that is width along the path. Here, the important thing to notice is the given question is a graph and it's also a bidirectional graph. And the next thing to be noted is the city with the smallest number of cities that are reachable through some path and whose distance is at most distance threshold. So the maximum value we can have is the distance threshold. And the final thing to notice, if there are multiple such cities, we have to return the city with the greater number. For example, if the city 0 and city 3 is also satisfying the same conditions, the city to be returned is the city 3, which is greater than 0. So consider this as a first sample test case, and here the given inputs are n equal to 4, that is the number of cities, and the edges, that is from and to, and the weight of the I is given, and the distance threshold is equal to 4. So the output is 3, and the explanation given here is the neighboring cities at a distance threshold equal to 4 for each city are city 0 equal to city 1 and 2. For 1 it is 0, 2, 3, and for 2 it is 0, 1 and 3. For 3 it is 1 and 2. From these 4 cases we can identify that the city with the minimum reachable cities are city 0 and city 3, which have 2 cities. So up from that, the city with have greatest number is written. So city 3 is the answer. The next sample test case is, in this the input is n equal to 5 and the edges are given, distance threshold equal to 2, and the explanation given is the neighboring cities at a distance threshold equal to 2 for each city are city 0 is 1, and for 1 is 0 and 4, for 2 it's 3, 4, and for 3 it's 2, 4, and for 4 it is 1, 2 and 3. From this, the city with minimum reachable city is city 0, so it is returned. The intuitive approach is, firstly we will be initializing an adjacency matrix called distance to store the distance between each cities. Initially all the distances are set to a maximum value, that is the infinity, except for the diagonal, because the distance from a city to itself will be 0 logically. So the diagonal will be set to 0, and then we populate the distance matrix with edge weights from the edges array. Since the edges are bidirectional, we set the distance for both the directions. After which, we applied the Floyd-Warshall algorithm to compute the shortest distance between all pairs of the cities in the graph. The algorithm iterates over all possible intermediate vertices k, and for each pair of vertices I and j, it checks if going through vertex k improves the shortest path from I to j. That is, the distance between I and j can be minimized if going through k. So the formula is distance of I, j equal to minimum of distance of I to j or distance of I to k and k to j. After which, we will be finding the city with the smallest number of reachable cities. So in this, for each city I, we count the number of reachable cities within the given distance threshold by iterating over all the other cities j. We update the min cities with the minimum number of reachable cities found so far and the result with the index of the city with the smallest number of reachable cities. If there are multiple cities with the same minimum number of reachable cities, we update result with the city index that has the greatest number. In simple terms, we have to find the city with the smallest number of neighboring cities and that have the smallest distance of less than or equal to distance threshold. For clear understanding of the code, before going to the coding part, we will first trace the code for this example. So we'll consider the graph as this one, and the given n value is equal to 4 and the threshold value equal to 4. Initially, the distance matrix will be full of zeros and we will be initializing it with infinity, after which the distance of city from itself will be set to 0, and then we will be populating the distance matrix with the edge weights from the edges array. Now we will be applying the Floyd-Warshall algorithm, which is to calculate the shortest distance between all pairs of the connected nodes. The steps for that is iterating through each cell of the grid and consider each cell as a potential intermediate vertex in the path, that is the k. For each pair of vertices I, j, we check if going through the intermediate vertex k leads to a shorter path or not. If the path through the vertex k is shorter, we update the distance between vertices I and j. We repeat this process for all possible intermediate vertices. As we update distances, the shortest path gradually propagate through the matrix. So in this case, the d0 value is 0, 3, infinity, infinity, 3, 0, 1, 4, infinity, 1, 0, 1, infinity, 4, 1, 0. After considering 1 as an intermediate value, the value of 0, 2 is changed to 4 because initially from 0, 2 we can't go directly, but after considering 1 as an intermediate node, we can go through 0 to 2 through 1, that is from 0 to 1 3 and 1 to 2 is 1, 3 plus 1 is 4. Similarly, the value of 0 to 3 is also changed through 1, that is 3, 0 to 1 is 3 and 1 to 3 is 4, 3 plus 4 is 7. After doing all these things, the final D3 matrix is 0, 3, 4, 5, 3, 0, 1, 2, 4, 1, 0, 1, 5, 2, 1, 0. So we will be iterating through the each cells of D3 matrix and we will be finding the city with the minimum number of neighboring cities that are reachable within the distance threshold. So firstly we will be initializing the minimum cities value to an infinity value and that is the result value to -1, and we consider a nested for loop I and j. The i's limit is from 0 to n, that is until 3, and the j's value will also be the same. So when I equal to 0, the reachable cities value will be equal to 0 and we will be iterating through the j's loop. For j equal to 0, the reachable city is 0 because the city cannot be considered as a neighboring city for itself. So whenever the diagonal cell is coming, we will be ignoring or we won't be adding any values to the reachable cities. And for j equal to 1, that is a cell 0, 1, the value of 0, 1 in D3 matrix is 3. So which is less than the distance threshold, that is a value of 4. So we will be adding +1 to the reachable cities. And for j equal to 2, the cell 0, 2, the value is 4, which is less than or equal to the distance threshold. So we will be adding 1 to the reachable cities. And for j equal to 3, the value is the value of 0, 3 is 5, which is greater than distance threshold. So we won't be adding any value to the reachable cities. After the single for loop j, we will be checking whether the reachable cities value is less than or equal to minimum cities and we will be updating it. So the reachable cities is 2, which is less than or equal to minimum cities, that is infinity. So we will be updating it to 2 and the result will be equal to the I value. I is 0 currently. and the next I value will be 1, where the reachabilities will again be set to 0, and we will be looping through j's loop. When j equal to 0, reachability will be 1 because 1, 0 is value 3, which is less than or equal to the distance threshold. We will be adding 1 to the reachable cities, and when j equal to 1, it is a 1, 1 cell, which is a diagonal cell, so we will be ignoring the case and will not add any values to the reachable cities. When j equal to 2, the cell 1, 2 value is 1, which is less than distance threshold, so we'll be adding plus 1 to the reachable cities. And for j equal to 3, the value is 2, so we will be adding plus 1 to the reachable cities. And now we will compare whether the reachable cities value is less than or equal to the min cities. Here the reachable cities value is 3 and the min cities value is 2, so it is not true, so we won't be updating min cities value, and we will be moving to I equal to 2. Again the reachable cities value is set to 0, so from 0 to 3 the j's loop will be running. Here when j equal to 0, the value is 4, and the reachable cities value is made plus 1 as it is less than or equal to the distance threshold. And when j equal to 1, the value is 1, so which is also less than or equal to the distance threshold, we will be adding plus 1 to the reachable cities. After which, when j equal to 2 and I equal to 2, it is a diagonal cell, so we won't add any value to the reachable cities. After that, when the j value is equal to 3, the reachable cities value is 1, so which is less than the distance threshold, so we will be adding plus 1 to the reachable cities. Again, now the condition is checked whether reachable cities value is less than or equal to the minimum cities. The reachable cities value is 3, which is not less than or equal to the min cities, that is the value 2, so the condition is false. After which the I is made 3, and again the reachable cities value is equal to 0. When j is equal to 0, the reachable cities value will be 5, so which is greater than the distance threshold, so we will not update any value to the reachable cities. After that, when j equal to 1, the reachable cities value is 2, which is less than the distance threshold, so we will add plus 1 to the reachable cities. Similarly, when j equal to 2, the value is 1, which is less than the distance threshold, so we will add the plus 1 to the reachable cities. And for j equal to 3 and I equal to 3, it is a diagonal cell as discussed earlier, so we won't add any value to the reachable cities. Now again the condition is checked whether reachable cities value is less than or equal to the minimum cities. The reachable cities value is equal to 2 and the previous minimum city value is 2, which is less than or equal to the 2, so we will update the minimum cities as minimum city equal to reachable city. So the minimum city value will now be equal to 2 and the result will be I. So there is the I value is 3, so the result value will be 3. So finally the result is equal to 3, that is the city with the smallest distance will be 3. In this case, we will be iterating from 0 to n, so the maximum number will be the final value, so we don't have to specify any specific condition for getting the maximum city value. So as discussed in the intuitive approach, the solution for this problem statement is this one, and here you can see the for loop, which is for filling the array with the maximum value, and the maximum value is divided by 2 and it is inserted to avoid with the overflow. After which the distance of I, I, that is the city to itself, will be set to 0 and the values of the edges are populated into the distance matrix. After which we will be applying the Floyd-Warshall algorithm, and the shortest distance between all the pairs of nodes are calculated. After which, as discussed earlier, 2 nested loops are run and we will be finding the minimum cities value and the result value. Finally, we will be returning the last return value, which is the city with the smallest number of neighboring cities that are reachable within the threshold values. The time complexity of this code will be O of n cube because the Floyd-Warshall algorithm runs for 3 nested loops, and the space complexity will be O of n square because the distance matrix is a 2D matrix, so it takes O of n square in the worst case. Now let us see the problem statement 2. So the problem statement 2 is given a Boolean 2D matrix The task is to find the number of distinct islands where a group of ones connected horizontally or vertically forms an island. Two islands are considered to be distinct if and only if one island is equal to another island, not rotated or reflected. The sample test cases, let us consider this grid. In this grid, the values are 1 1 0 0 0, 1 1 0 0 0, 0 0 0 1 1 0 0 0 1 1. So here there are two islands, that is 1 1 1 1, and the last four cells, that is 1 1 1 1. Here both the islands are looking similar without even rotating or reflections. So these both islands are considered to be a single island and the output will be 1. And the next sample test case is, consider this grid 1 1 0 1 1, 1 0 0 0 0, 0 0 0 0 1, 1 1 0 1 1. The output for this grid is 3, and the explanation here is the red color ones are considered to be one island, and the green colored ones are considered to be one island, and the blue colored ones are considered to be one island. Here there are two green colored ones, in the first row and in the last row. They both are considered to be one island because they both are looking similar without even rotating and reflection. But whereas in the first red colored ones and in the blue colored ones, if we rotate the red colored ones for twice, we will be getting the blue colored ones, which is taking two rotations. So this is not considered to be a distinct islands. Now let us see the intuitive approach for this problem statement. Firstly, we will be defining a method called num distinct islands, which takes the 2D grid of characters representing a map as input. The goal is to find the number of distinct islands in the grid. Here, an island is a connected component of ones that is surrounded by zeros, that is the water. We initialize a set called shapes to store the shapes of distinct islands encountered, because the set won't allow duplicate values. Then we will be iterating through each cell of the grid. If we encounter a 1, that is the land, we start for depth first search, DFS, one of the traversing algorithm used in graphs to explore the entire island's shape. For each island, we maintain a unique shape representation using a list of pairs, that is the x offset or y offset, also known as x base value or y base value, which is the reference value to represent the relative positions of each cell within the island. After DFS travel, we add the island shape to the shapes set. Finally, we return the size of the shapes set, which represents the number of distinct islands. And then now let us see the DFS method. This method performs a DFS search to explore the shape of an island starting from the given cell I, j in the grid. It takes the grid current cell coordinates, that is the I and j given by the function call, and base row and column indices to represent the starting cell of the island, that is the reference values, and a list of pairs to append the shape representation. If the current cell is out of bound or represents the water, or it has been already visited, the function call will be returned. Otherwise, we add the relative position of the current cell to the shape list as a pair of I minus base row, j minus base column. The thing why we are doing this is very interesting, and we will be seeing that in the tracing of the problem statement. Then we will mark the current cell as visited by changing its value to 0 to avoid revisiting it. And finally, we recursively explore the neighboring cells in the order of down, up, right and left to continue building the shape of the island. The order can be of any order, but it should be the same for the entire code. Now let us see the tracing for the given grid. The input is grid equal to 1 1 0 0 0, 1 1 0 0 0, 0 0 0 1 1, 0 0 0 1 1, and the rows equal to 4, that is the row value equal to 4 and number of column equal to 5. We will initialize a set to nil initially, and we will be adding the shape value to the set, and then we will iterate through the cells of grid using a nested loop of 2 loops. Here the inner loop will be running till the number of columns and the outer loop I will be running till the number of rows. Initially when I equal to 0 and j equal to 0, we will be checking whether the value is equal to 1. If it is equal to 1, we will call the DFS function. So here the value of 0, 0 is 1 and we are calling the DFS function with the inputs grid, the value of I, j, that is 0, 0 and the current cell value which is used for the reference positioning 0, 0 and the shape which is a array list. And in this DFS call we again tend to call 4 kinds of DFS, that is for down, up, right and left. First we will be calling the down DFS call with the inputs grid and the down cell value will be I plus 1, that is 0 plus 1 will be 1 and the j value will remain same, so it is 0 and the reference values are 0, 0 and the shape array list will be passed. So in this the relative positions will be calculated, that is I minus x base value and j minus y base value, that is 1 minus 0, 0 minus 0. So 1, 0 will be added into the shape array list and the grid value of 1, 0 will be made 0 to avoid the revisiting. And this condition is satisfied. So again inside the down DFS call we will be calling 4 kinds of DFS, that is down, up, right and left again. So in the down DFS call the values of I and j will be I plus 1, so 1 plus 1 will be 2 and j remains same, so it is 0 and the reference values are 0, 0 and shape array list is passed. In this case the DFS is returned as the grid value of I, j, that is 2, 0 is equal to 0, so that is not equal to 1, so the function call is returned. After down we go to the up DFS call. So in the up DFS call the value of I will be I minus 1, so the initial value is 1 and 1 minus 1 will be 0 and the j remains same, so it is 0 and the reference values are 0, 0. Finally the shape array list is passed. In this case also the function is returned because the node 0, 0 is already visited. After the up DFS call we will call the right DFS function. In the right DFS function we will be checking whether the function node is already visited or the grid of I, j is not equal to 1 or it comes under the boundary. So if all the 3 cases are not satisfied, we will be going into the DFS call and the relative position of 1, 1 is added into the shapes array list, after which the grid of 1, 1 is made 0. The relative position for this DFS call is I minus x base, j minus y base, which is 1 minus 0, 1 minus 0. So 1, 1 is added to the shape array list, after which the grid of 1, 1 is made 0. Within this right function we again call the DFS calls for down, up, right and left. In the down DFS call the inputs are grid 2, 1, 0, 0, shape. For this the grid of I, j is not equal to 1, so the function is returned. And in the up DFS call the inputs are 0, 1, 0, 0, that is 0, 1 is the ij and 0, 0 is the reference values and the shape array list is passed. So in this case the 0, 1 is not visited as well as it is within the boundary and the grid of I, j is also equal to 1, so we will be going into the DFS call. And for better understanding the down will be I plus 1, j and for up the values will be I minus 1, j and for right it is I, j plus 1, for left it is I, j minus 1. So in this case the value the DFS call is up, so the value given here is 1, 1, so it is up, so 1 I minus 1 and j will be the up value, so 1 minus 1 is 0 and j remains same, so 0, 1 is passed as input and in this the grid of 0, 1 is made 0, after which the relative position of 0, 1 is added to the shape array list. So I minus x base, that is 0 minus 0 and j minus y base, that is 1 minus 0 is added into the shape array list. Now we get those 4 values of the ones 0, 0, 1, 0, 1, 1 and 0, 1. These are the relative positions of those 4 ones from 0, 0. Within this up function, we will be calling again the DFS call for down, up, right and left. In the down DFS function, the input given is 1, 1, which is already visited, so it is been returned. And for up DFS call, the grid value is minus 1, 1, so which is not under the boundary, so we'll be returning it. After which the right and left condition will also be returned due to grid of I, j is not equal to 1 and the 0, 0 value is already visited. So after computing all the relative position values for those 4 ones, we'll call the recursive calls for all the remaining functions, but all those functions will be returned either by those 3 cases, that is grid of I, j is not equal to 1, or the node is already visited, or the given input value won't be in the boundary case. So now the DFS of right is called. Here the function is returned due to grid of I, j is not equal to 1, and in the left DFS call 1, 0 is called, which is already visited. Again in the outer DFS call, the left, the 1, minus 1 value, which is not in the boundary case, so that function is also returned. In the last thing, the outermost DFS is going to be working. So initially we are working in the down part of the first DFS call, so the remaining things up, right and left are going to be executed now. In the up DFS call, the values given are minus 1, 0, which is not inside the boundary, so the DFS call is returned. And in the right DFS call, the inputs given are 0, 1, which is already visited, so the function will be returned. And in the left DFS call, the inputs given are 0, minus 1, which is not inside the boundary, so we will be returning it. Finally, the shape array is added into the shapes set. So after which we'll again iterate through the nested loops, and until we get 1, we'll be iterating. In 2, 3 we get 1, so we again call the DFS function with the input values 2, 3 and the reference values 2, 3, and a new shape array list is sent. Again there the row value and column values are calculated, but we are in not need of that part, so the value of grid 2, 3 is made 0 to avoid the revisiting, and again the relative position of 2, 3 is added to the shape array list. After which inside this DFS call we are calling 4 DFS calls, that is down, up, right and left. So now first we go into the down DFS call. In the down DFS call, and the values are 3, 3 and the reference values are 2, 3, which will be same until the complete execution of this particular DFS for the index value 2, 3. So in the down DFS, the grid value of 3, 3 is made 0 to avoid the revisiting, and the relative position values are added into the shape array list. The relative position will be in this case the given I value is 3 and the x base value is 2, so 3 minus 2 will be 1, and the j value is 3, the y base value is 3, so 3 minus 3 is 0, and then this 1, 0 is added into the shape array list. After which inside the down DFS call we again have 4 DFS calls, that is down, up, right and left as discussed earlier. And in the down DFS call, the function is returned because the value 4, 3, which is the down value of 3, 3, that is when we add plus 1 to 3 we will get 4, and the j value remains same. So the down DFS function is called with the I and j values of 4 and 3 and the reference values 2, 3. Again this case the boundary case is violated because the row value should be less than 4, but in this case the value of a row is, that is the I value is 4, so it is violated, so we will be returning it. And in the case of up, the value of input is 2 comma 3 and the reference values are 2 comma 3. The function is returned because 2 comma 3 is already visited. And for the right function call, the input value is 3 comma 4 and the reference values are 2 comma 3. In this case the boundary case is satisfied, as well as it is not visited earlier, and the value of 3 comma 4 is equal to 1. So we will be going to the DFS call. Inside the DFS call, we will be making the grid of 3 comma 4 to 0, and we will add the relative position of the 3 comma 4 to the shapes array. So the I value is 3 here, and the x base condition value is 2, so 3 minus 2 is 1. Here the j value is 4 and the y base condition value is 3, so 4 minus 3 is 1. So we will be adding 1 comma 1 to the shape array list. And in the right DFS call, we call the DFS call for down, up, right and left. For down, the input value is 4 comma 4, which is violating the boundary case, so we are returning the function. And next we will be calling the up function. In this up DFS call, the input value is 2 comma 4, which is not violating any of the rules, so we will be going into the DFS call, and the relative position value of the current cell is added to the shape array list. The relative position of the current cell here is I minus x base, that is I value is 2 and the x base value is 2, so 2 minus 2 is 0, and the j value is 4 and the y base value is 3, so 4 minus 3 will be 1. So 0 comma 1 is added into the shape array list. And for this up DFS call, again there is 4 sub DFS calls, that is down, up, right and left. But for all the DFS calls remaining, the function calls will be returned either by any of the 3 cases, that is the boundary case, or the cell will be already visited, or the cell value will be 0. So we not needed to work out for all those things, and the shape value now will be 0 comma 0, 1 comma 0, 1 comma 1 and 0 comma 1. After the DFS call execution, the shape value will be added to shapes set. But in the shapes set, already 0 comma 0, 1 comma 0, 1 comma 1 and 0 comma 1 is existing. The value won't be inserted. So now the size of the set, that is the shapes set, will be giving the number of distinct islands, and the size of the set is 1, so the number of distinct islands is 1. Here the points to be noted here is, as I said earlier, the direction of order of traversal should be same. Only then we can find whether the island is distinct or not. If in case let us consider the first time you are calling as down, up, right and left, and second time you are calling as right, left and down, up. So first time when we call down, up, right, left, we will be getting the shape array list as 0 comma 0, 1 comma 0, 1 comma 1 and 0 comma 1. And for the second time when we call like right, left and down and up, we'll be getting as 1 comma 1, 0 comma 1, 0 comma 0 and 1 comma 0, which is different from the previous set value. So the set will allow the value to be inserted, and the number of values present in the set will be 2, which will make the chaos. So the direction of order of traversal should always be the same. Now let us see the coding part of this problem statement. This method is used to iterate through the grid matrix and used to call the DFS function, and here only we will be adding the shape value into the shapes set, and finally the shapes size will be returned as the output. And this method is the DFS method. Here the conditions are I is less than 0 or I is greater than or equal to rows, which is the boundary case for rows, and for j less than 0 and j greater than or equal to 0, which is the boundary case for j, or the grid value not equal to 1. This grid value not equal to 1 checks for 2 conditions, that is whether the cell is already visited or not, or the cell contains water or not. So if any of these conditions is satisfied, we will return the function, and if not, we will go into the DFS call. We will find the row value and the column value. Instead of finding the row value and column value again and again for each DFS call, we can also declare a static variable called row and a column, and we can initialize the row value and column value to it. And once we enter into the DFS call without getting return statement, we have to make the cell value to 0 to avoid revisiting, after which the relative position value of the current cell to be added into the array list. Then the 4 recursive calls down, up, right and left is called again and again until the entire DFS call is getting completed. Here, coming to the complexity part, the time complexity is O of m star n plus k. Here the m represents the rows in the grid and the n represents the columns of the grid. So while we traversing through the entire grid, it takes m cross n in the worst case, and we are using hash set for storing the list values. So if there happens any kind of collisions, we have to resolve it, so it can degrade the time complexity to O of n in worst case. And so totaling of these two things, we get the value of O of m star n plus k. And the space complexity is also the same, that is the O of m star n plus k. Here, when we use a hash set for storing the distinct shapes, it takes O of k space complexity, and during DFS traversal, the recursion stack might contain up to O of m star n elements. So combining these two, we will get O of m star n plus k. If the tracing of the algorithm is not clear, watch the coding part of this problem statement and go through the tracing. Or if the coding part is not clear, watch the tracing part of the algorithm and go through the coding part. The reference for these codes are given in the Google Docs and the link is provided. And still, if there is any kind of doubt, you can leave me a message in the comment and I will be replying on it. The reference video which I saw is given below, as well as the reference materials, that is the tracing of the algorithms is also given, and you can use that for further references. Finally, as we conclude our session, we have journeyed through the intricacies of 2 challenging problems and unveiled their solutions using Java programming. I hope you found these insights valuable and insightful, offering new perspectives on problem solving techniques. Remember, coding is not just about finding the solution, it's about the journey of discovery and continuous learning. Thank you for watching and have a great day ahead.